Have you ever heard about spooky action at a distance? You might have thought that the phrase corresponds to quantum entanglement, but there are actually more concrete phenomena that stand closer to us. Consider the low and high tide, for example. The moon pulls the seawater upwards with its gravity, thus causing the seawater surface to rise and fall. This is a perfect example for a physical concept called the force field, where an object exerts an action to another object without directly touching it. Force field belongs to physical and mathematical concept called vector field. The inner mechanics of any vector field is hidden from plain eyesight. Understanding it requires a strong knowledge about vector calculus, in particular the gradient operator, divergence, and curl. In this video, we will explore basic concepts about those operators with the aid of visualization and the cases where they are applied. This journey begins with partial derivatives. Consider a continuously differentiable one-dimensional function. Because it has only one free variable x, there exists only one differentiation scheme, which is with respect toward x. If its first derivative is overlaid on top of the function plot, the first derivative tells us in a really obvious manner that it represents the rate of change of the function. What happens to the derivative if the function doesn't just have one free variable, but 2, 3, or more? In the two-variable case, the differentiation is extended by partial derivatives. The partial derivatives come from taking the derivative of f with respect to each variable separately. The total derivative comes from addition of the x component and the y component. Unfortunately, plotting the total derivative is quite an impossible task because it has no obvious shape to draw. This is where the directional derivative, or the gradient operator, comes to the rescue. The gradient operator deals with x component and y component differently. Instead of putting dx and dy behind the partial differentiations, it puts unit vector of x and y before each partial differentiation. Let us take a surface, for example, which is described by its height z as a function of x and y. When coupled with the function, it finally generates something that can be drawn, a vector field. The x component comes from the partial differentiation with respect to x, and the y component from the partial differentiation with respect to y. This vector field can be overlaid on top of a contour map of the function. At any value of x and y, the directional derivatives will tell us where to go. These arrows, being perpendicular to the contour lines, actually point to the direction of steepest ascent at any x and y coordinate point. At this point, we should learn the definition of a scalar and vector field. In simple language, a vector field assigns a vector to each coordinate point in space. Take the electric field as an example. For each point in space, there is an arrow that indicates which direction the electric field points to and how long the arrow is. The length of the arrows represents the magnitude of the electric field, which is governed by Coulomb's law. Another example of vector field is the gravitational field. The Sun exerts a force on each planet according to Newton's law. Gravity is an attractive field, not a repulsive one, so the planets are pulled toward the Sun in their orbits. A scalar field assigns a scalar value to each coordinate point in space. An example of this is the electric potential field. Instead of using vectors, it uses scalar to describe the electric field in the region of space surrounding the electric charge. In the previous example, the surface is the scalar field, while its gradient is the vector field that corresponds to the scalar field. The gradient operator for 3D space has an extra term that calculates the partial derivative with respect to z-axis. Take the electric field of a positive point charge as an example. Its electric field points outward, while the electric potential gets stronger as we get closer and closer to the charge. The electric field is the vector field, while the electric potential is the scalar field, and we can compute the electric field by taking the negative gradient of the electric potential. Now that we have a vector field, we can ask, locally, does this field act like a source, a sink, or just passing through without piling up anywhere? This question is exactly what a divergence measures. The divergence operator works differently to the gradient operator. It does not work on the scalar field, but on the vector field by means of dot product. The partial differentiation with respect to x only works on the x component of the vector, and so are the partial differentiation with respect to y and z. It spits out a scalar field for the region where the vector field exists. Picture a different kind of vector field. Instead of electric field or gravitational field, imagine the velocity field of a fluid. At every point, the tiny arrow shows the velocity of the fluid. Then pick a tiny box around the point. If more vectors leave the box than enter, the point behaves like a source with positive divergence. If more vectors enter than leave, it behaves like a sink with negative divergence. If inflow equals outflow, there is no net accumulation, the divergence is zero. The previous example can be easily translated for a static electric field. A positive charge acts as a source with positive divergence, from which the field lines are born. In contrast, a negative charge acts as a source with negative divergence, to which field lines die. In empty space with no charge, the divergence of electric field is zero, consistent with the absence of source or sink there. Having worked with electric field, I'd like to introduce a new field, namely the magnetic field. For now, consider a wire with a current running on it. Viewing the field lines, it becomes apparent that there is no inflow or outflow at any region of space. Therefore, in contrast to the electric field, the divergence of any static magnetic field is zero. Up to this point, we have explored gradient operator, which indicates the steepest change, and divergence operator, which measures whether a vector field behaves like a source or a sink. There is one more key behavior. Does the field have a tendency to rotate? This is what the curl operator measures. The curl operator acts upon a vector field in a really different way, and perhaps this is the most complex. We have to calculate the determinant of a 3x3 matrix, with the first row containing the unit vectors, the second row the partial differentiation operator, and the third row the field functions. To reduce the complexity and make the examples more understandable, we will resort to two-dimensional cases. Consider a turbine that is submerged in a water flow. The flow of the water will directly affect the movement of the blades. If the blades start rotating, the curl in the region surrounding the center of the turbine is not zero. According to the right-hand rule, the angular velocity vector is directed downwards, indicating a clockwise rotation. The direction of the curl is the rotational axis of the turbine, while the magnitude tells us how fast the blades spin. In contrast to the divergence operator, the curl operator spits out a vector field when given a vector field. Now let us extend the concepts mentioned before to electric and magnetic fields. Obviously, we cannot make an electric field or a magnetic field to drive any rotation, but we can visually see whether the field has any rotational component or not. For a static electric field, its curl is zero, but its divergence is non-zero. In contrast though, for a static magnetic field, its curl is non-zero, while the divergence is zero. If you want more content like this, don't forget to subscribe to us so you won't miss our next content. What do you think I should discuss next? Tell me in the comment section. Thank you and see you next time.